Okay, so let's get started. So just wanted to show you really quickly the statistics for the exam. It shows max, average, median, and mode, as well as standard deviation, just to get a typical to see or to have a comparison purposes for what you've done. I can't show you much more than this because this will reveal private information about students, but this is the general class, which I think this information should be available to you in your grade book. I think you can look at the statistics. I have that set up so you can do that. Pardon? All right, shall we go over the test? So on what's called a normal distribution, the standard deviation is if you're within one standard deviation of the mean, then that is like 63% of the folks are meeting that criteria. And then if you're in two standard deviations, then it's like 97% or something like that. So it's usually just a way of doing a statistical analysis to categorize what people would, most people would be in that range. So it's based on what's called a normal distribution. Some people use it if you're within one standard deviation, you're pretty close to the average. If you're within two, you're either exceptionally well or exceptionally poor. And then if you're beyond that, then you would either be gifted or for some reason didn't get the material. So usually most of us would fall within 1 to 2 standard deviations of the average on anything, height, weight, whatever it is. Okay. All right, before we start going over the test, any questions or concerns about it? I heard a couple of people say that time was a little bit of an issue on this one. Is that a fair statement?
Yeah, I was a little bit pressed for time at the end.
Okay. So maybe take off some of the parts. I know some of the questions you can see, like there's a lot of parts, but what the thing is like to go through the material, they're usually really quick answers, right? Except for the part where you had to do the Thevenin stuff. Most of that was 1 or 2, one equation and you got the answer essentially. What about the content? Was it what you expected? More or less? Okay. And then also the exam review. Do you feel like the third exam review helped you better prepare for this one? Or did you not really notice a difference? It's okay if you didn't. It's just, I'm just curious to see where we should put the focus. Okay. Any other thoughts, discussions, or just jump right in? Okay. Well, let's just jump right in. So everybody should have your test. If you did it online, you should be able to access it. Problem number 1. 74, I think it was 74.1. I had it up on the board at the beginning of class. So we have a 50 horsepower. And again, this is rated. It's not actual. And it's 873 RPM for full load. Immediately, you should be able to look at this and tell me how many poles?
8.
8-pole machine, because we know 3,600 is 2 poles. 1,800 is 4 poles. 1,200 is 6 poles. 900, and that's synchronous speed, is 8 poles. And the equation that we have is synchronous speed is 120 times the frequency divided by the number of poles. We know that an induction machine can't operate at synchronous speed. It has to be less. So the next nearest synchronous speed for 60 hertz is 900. So if you needed to do the calculation, you could have just plugged it in. B was percent slip. which is equal to 100 times sink speed minus mechanical speed over the sink speed. Okay. I don't think we need to do the calculations, but if anybody wants to see that, let me know. That was it for number 2 or part B. All right, so C is the slip frequency of the motor. That's the rotor frequency. It's the same thing as the slip frequency. Take your electrical frequency, multiply by the slip, and you got your rotor frequency. All right. Now, this is when I wanted you to put your thinking caps on. And we talked about this a lot, okay? It was exhaustive how much we talked about it. But we tried to give you enough detail so that you could solve the problems just by contemplating. Now, the speed of the rotor field with respect to the stator. What speed does the rotor field spin at? Spin at synchronous speed. It has to spin at synchronous speed because our induction motor wants to output constant torque. And since the AC field or the stator field, as a result of the AC current flow as at synchronous speed, for those two to maintain a constant torque, they have to spin at the exact same rate. And if you also recall, the reason why you get a rotor field that is spinning at the synchronous speed is because on the rotor itself, you have an AC waveform. Anytime you have like inductors don't work on DC, right? They work on AC because you have to have a constantly changing magnetic field to go ahead and have it function. Otherwise, it's just a short circuit. So that constantly changing magnetic field creates a constantly changing current. And so it's the same thing over here. It has to have an AC frequency. So the frequency on the rotor, you can convert that to a synchronous speed, just like what we did on the stator. Remember how we took a 60 hertz three-phase set of windings? If you take the same thing and instead of running it at 60 hertz, run it at 1.8 hertz or whatever it is, you're going to get a speed, a rotational speed, that's going to be the actual slip speed that you would get. So when you add the fact that the rotor is spinning at mechanical speed, plus the fact that you have an AC current or 3 AC currents spinning around, and then that's creating a magnetic field, that's how the difference is made up. Those two speeds make up the difference. So here's E, here's part F. The speed of the rotor field with respect to the stator speed, stator field, they're spinning at the same speed. 0. Yes, sir? The rotor field is spinning at synchronous speed. The stator field is spinning at synchronous speed, right? We have to maintain constant torque, so they must spin at the same speed. So there's no difference in speed. That's part E, is with respect to the stator field. Oh, did I skip a part? Yeah. So E is the respect to the rotor field with respect to the stator. The stator's not moving. That's 900 RPM. The stator field is rotating. That's spinning along at synchronous speed. The rotor's field is also spinning at synchronous speed. So the speed difference between the two, it's like a car when you're on the highway, you're doing 65 miles an hour and you're looking at somebody, they're doing the same speed. You could almost have a conversation, right? You're going the same speed, so you don't notice a relative speed difference. That's the concept. Okay. G was the shaft torque at full load. I'll just give you the equation. It's outputting max power, 50 horsepower. Make sure you convert that to watts and make sure you convert 873 RPM to radians per second. If you want to get torque in Newton meters, it's just unit conversions. That's all it is. Yes, sir. Did I skip D? Oh, sorry. Yes, I did skip D. The speed of the rotor field with respect to the speed of the rotor field with respect to the rotor itself remember the rotor is spinning at mechanical speed. The rotor field is going to make up the relative speed difference because the rotor field is spinning at synchronous speed. So 900 RPM minus 873 RPM is the difference. You also could take 1.5 hertz. Remember that? If you take 1.5 hertz, and if you plug that into this equation, what do you think you're going to get? Let's try it. 120 multiplied by 1.5 divided by 8. So 120 divided by 8 is, what is that? That's 440. Not 40. It's 60 over 4 times 1.5. And then that's 60 divided by 4 is 15 times 1.5. That's, what is that? It's 15 plus half of that. So that's 22.5. That's off a little bit. I'm not sure why. Oh, I know why, because it's not actually, no, wait a minute. Is that 1.5? 1.8 hertz. That's my problem. If you did at 1.8 hertz, guess what you'd end up with? 27. Let's check it out. Let's bring up MATLAB. You can try it in your calculator, but 15 times 1.8, so that's 15, and then 0.8 times 15 or 4, that's 9, isn't it? Correct? Am I doing that correct? Too quickly? 15 times 1.8 is 9. Yeah, so I'm just breaking up the numbers, but we'll just do it here quickly in MATLAB. Where'd MATLAB go? Here it is. So 1.8. It must be still launching. Times 15. 27 RPM. So either one would have given you that answer. You could have used the rotor frequency and recognizing, and we talked about this, this is maybe a little more subtle, but we always said that in an induction motor, the number of poles that you have has to match on the stator and the rotor. Same thing for a synchronous machine. So you always have the same number of poles on the stator and the rotor. Okay, and that's it for one. G, I got 408 Newton meters. Okay, well, see me up. Yeah, bring it up and I can look at it. Any more questions on number one? Fair, not fair? Pretty straightforward. Do you feel like you were prepared well enough for this particular problem?
Yeah, I feel like we went over this pretty coherently in class.
Okay. Is there different wording I could have used that would have made more sense when writing the question? Pardon? You don't like words? Fair enough. Yeah, if there's any suggestions on how to improve the wording, but I wrote that specifically with respect to the rotor itself. You remember how I talked about being a bug sitting on the rotor and looking at references? I tried to give you that if I'm standing on the rotor or if I'm standing on Earth and the sun rises and all that stuff, we use the same concept. So instead of saying stationary or rotating, I tried to actually put it to that, that sort of commonality, hoping that that would help. But if you have suggestions on how to improve the wording, I'm all for it. All right, number 2. So I don't care about the 25 horsepower because I know what the current is. So I know that it's a 3-phase machine. It's 208 volt. It's 75 amps. And it's at a 0.85 lagging power factor. Then I've got a bunch of losses. And so instead of putting them over here, I'm actually going to do my curve. So this is my P in, which is equal to the square root of 3 times my V line, 208, times my I line, 0.85. And notice when I'm putting the current in there, I'm doing it as a magnitude and an angle. So you want to make sure that you put the real part of this, or else you're going to get goofy results, right? So your P in should only have a real quantity. Now I'm going to go ahead and start dropping my power. So this is my stator copper loss. That's equal to 1867. Continue on. I'm going to lose my core losses. P core. Continue on. Now I'm going to lose my, because at this point, I've gone from the stator to the rotor. So here is my air gap power. It's jumped between the stator and the rotor. So that means it's gone through the air gap. It's not mechanical power yet because I still have some losses. What are my losses? My rotor copper loss. Now, there's no more electric losses, electric power losses that I need to take into account. So that is my converted power. I have one more loss, and this is because we live in the real world and we have friction and windage. So my friction and windage losses is 300 watts. And then the rest is P out. Okay. So it asks for P air gap. What's P air gap? It's P in minus the stator copper losses, minus the core losses. Then it says mechanical power developed, not output, but that's developed mechanical power. So this P converted is the same thing as P developed. So my developed power, I can see over here, the only thing that I need to do is remove from my air gap my rotor copper losses. Okay. The next thing it says is P out, because when it says shaft output power, hopefully, you know, everybody knows it's just output power. That's going to be equal to my developed power minus my friction and windage losses. And then the last thing for this problem is efficiency, just P out over P in. Some of the students really struggled with this problem, and I'm not sure how to present it differently that it makes more sense. Because I think when we did these problems in class, I always suggested go ahead and do your power flow diagram, right? Take your P in and start subtracting out your power. If you're not sure where they go, and if you're better with circuit analysis, do your equivalent circuit diagram. This is R1. This is R core, JX1, JXM, JX2, R2, and R2 times 1 minus S over S. My stator copper losses come from the windings in the stator. My core losses are over here. My rotor copper losses are over here. At this point, this electrical circuit can't do any more for me because I can't include mechanical losses, right? I can certainly get my P converted at this point. And I can even get from this diagram the power that jumps across the air gap, if you will, right? But I can't get the output power because that's mechanical output. And for most of us in electrical engineering, we haven't figured out a way to capture those mechanical losses. There are ways to do it that you can model it mechanically, I mean electrically, but we haven't really done that. that's a separate class. So thoughts on how to improve how to accomplish this one, because this one, there are a few people that struggled with this one. Okay. Where they belonged.
Yeah, to kind of figure that out, but once like I could see it and understand what it was actually directing at, it made it a lot easier. Because at first I was like, just a random letters and stuff.
Right. It's not easy to figure out what goes where, right?
Yeah, once I was able.
Yeah. Sure. Or should we hold it against him because he came in late? Make him guess.
My 10.12.
Hey. Do we want to do a poll, an anonymous poll, or does everybody want to be like, Chris, sorry, bud, but. So yeah, so I mean, like I said, when we were tackling these problems in class, as much as I could, I encourage you to draw the actual flow of power through the machine, because I also think it gives you a pretty good understanding as to what's happening, especially when we look at operation of an induction motor. It really helps us do that. And then if you recall, when we looked at synchronous machines, we also did something similar to this as well. We didn't really do that in transformers, because with transformers, we only have to characterize electrical losses. So we could just do that in a circuit diagram. But once we start getting into mechanical losses, this is kind of like the world where our mechanical engineering friends can actually talk with us, right? Because if you tell them, hey, look, I've got this input power, it's 50 kilowatts. And then I'm dropping this power, this power, this power. Mechanical engineers understand power losses really well. But once you start drawing the circuit analysis part, they might not necessarily see, I don't see where the rotor copper losses are. They might miss that part. But they don't need that by putting this diagram, and then also by putting the different, locations. What is air gap power? What is converted power? What is output power? That hopefully makes a little more sense. I will tell you, once you get out in industry, the more diagrams you can do, the better. Picture tells, they say 1,000 words. It's probably like 1,000,000 words. I can't tell you how many words I've written, and a picture. I could write the world's best document, and if I didn't have a bunch of pictures and figures in there, it just doesn't make sense. It just helps people see things and make a better understanding of it. All right, shall we move on to number 3? Because number 3 was a circuit diagram. R1. I'll do this one a little bit clearer. I did not give you a value of R sub C, so we're going to neglect it. This is JXM. Oops, I forgot my X1. Sorry about that, folks. JX1. This is my JX2. This is, and it depends, right? You can combine these in one value or not. It's totally up to you. I normally would put it this way. R2 times 1 minus S over S. But then what I would do is I would kind of do this combination thing to show that that's just R2 over S. So if I had to do circuit analysis, I would simplify my life a little bit and show what the combination, what the results of that would be. All right. So now you know that the applied voltage was 480. And you could have done it either way, 480 over square root of 3 or not. But we typically have done it so that it's 480 divided by the square root of 3. That'd be an individual voltage. And then it says you've got a slip equal to 3.33%. My rotational losses, so that's friction and windage, is 2950. Number 1, find NM. Oh, I forgot to tell you, it's a 4-pole motor. So if you recall, my slip percentage was equal to 100 times NS minus NM over NS. And we also said that NS is equal to 120 times my frequency over the number of poles. You should be able to solve this equation for NM, right? I know it's 60 hertz. I know it's a 4-pole machine. 1800 RPM is the synchronous speed. I plug that into here. I should be able to pull out my mechanical speed of operation. Okay. Now that was an RPM. If you wanted to do radians per second, that's just a unit conversion. That's an extra step. For part B, this is up to you. You could have certainly have done the Z Thevenin approach and did that way. Right? And solve for that way because it was saying, what is the stator current? Solve for I with this. Or you could have done it what we did in class and did the loop equations, which is what I included in your that exam review document, right? Remember the exam review document? We did it that way, but you also could have done the Thevenin equivalent. Does anybody want to see the loop equations that I would write? Or do you feel like it's beating a dead horse?
Paul, you had in the for the
Go ahead, Pete,
Thevenins. Sorry, yeah, for the Thevenins equivalent on the review that I2 is what you'd be calculating, which from the other diagram, I2 is the rotor current.
Yep, that's correct.
So with the Thevenin, how are you supposed to figure out the stator current if the current in the Thevenin is?
No, this right over here, I would convert that to a Thevenin equivalent impedance there, right?
Oh, okay.
So I would do series parallel combinations to do that one.
Right, I follow.
Okay. Yeah, because the other way, it's reflecting things from left to right. This is trying to get it from the other direction. So it really just depends on which way you want to go. I personally, and I can tell you over the course of your career, doing series parallel combinations is a lot of work and you don't get a lot of bang for your buck. You lose out on information. You're almost always better off to not combine elements. Okay, unless they're really like in series, if it's just a real series one, most of your circuit analysis moving forward in your career is you'll just write, you know, let's see, V1 over the square root of 3 or V phase or V line, I should say, 0 is equal to your impedance matrix times your current matrix. Anybody want to guess as to why you find that this one's more effective? It's not an obvious answer.
We have
but it is what they'll tell
computers.
you why. What's that?
We have computers that can do it.
Computers will do that. If you ask a computer to go ahead and figure out if something's in series and parallel, it can't look at that and see that they're in series and parallel. What a computer will do is it'll just say, oh, I have a node over here. That's node 1, node 2, node 3, node 4, node 5, and basically do nodal analysis to solve all this stuff. Because having something that's got 10 million nodes is no problem for a computer. For us, it's a lot of work, but for a computer, it's no big deal. So if you're going to do anything with systems analysis with power systems, they do nodal analysis, and we'll learn that next semester how to manage that. But it's much easier for a computer to not try to do series parallel combinations. If you asked a computer, go ahead and tell me the Thevenin equivalent impedance, which is something you do on the power system all the time. How do you think that they would calculate the Thevenin equivalent impedance? We talked about it in this class. Maybe not this class, the other class. If I know the voltage and the current, isn't Z Thevenin equal to V Thevenin divided by I Norton? You solve for current using whatever nodal analysis technique you want, and then you just solve for Z. Very basic. So they're not sitting there doing combinations and turning power supplies off and doing all this stuff. They're just like, I'll just calculate what the current is. Once I know the voltage, I got the current, I'll give you Z. There's no guesswork, essentially. So that's the stator current, and then a lot of people forgot. There's two parts to the current, right? Right? There's the magnitude of the current and the angle of the current. We're in AC here. We can't just get by with the magnitude of current. You got to know the angle. You may not always use it, but you've got to have the angle. And if you remember the previous problem, it said 75 amps at a 0.85 lagging power factor. How would you have been able to do the previous problem if you weren't given the power factor? You couldn't have done it. It's not feasible. So I've tried to be consistent, and I know it's probably annoying, but I hope you understand why I've been harping on that so much. Voltage and current must have magnitude and phase. It'll really start to trip you up when you get into more advanced circuit analysis with AC. Okay. All right, continuing. The power factor. Why is it the cosine of theta S? Because my voltage magnitude is at an angle of 0. Technically, the power factor is the ratio of P over S, right? But that's also the same thing as the impedance angle, which is V divided by I, which is equal to V at an angle of 0 divided by I at an angle of theta. So that's equal to V over I, 0 minus theta. The only thing I have left is the cosine of theta. So that's why it just happens to be cosine of theta, but it's only if you have an angle of 0 here for your voltage. Now, the next step is to do a, geez, I can't talk. You can either do the diagram where you have the powers dropping off, totally up to you, or you could have gone ahead and once you know I stator and I rotor, the question is, what is the developed power? P developed is the mechanical power is equal to I R magnitude squared times R2 times 1 minus S over S. Right? So you could have tried to go, here's Vn, and started subtracting losses, but this one's a little harder because now what I need to do, whoops, is I've got my stator copper losses over here. No core losses, so I didn't worry about it. I've got my rotor copper losses over here. So I would have had to calculate those. Whereas in this case, I didn't need to do that. You certainly could have done the Thevenin equivalent approach where you did it as a function of S and did it that way. But to me, it seems like it's more intuitive to just do these calculations. So that's my developed power, and then P out is my developed power minus my mechanical losses. Questions on that? So far, so good. So my developed torque is P developed divided by omega sub M. And my output torque is P out divided by omega sub M. Once you have the two powers, you just divided them by your rotational speed, and you know your rotational speed, remember, because you had your slip, that was it. Motor efficiency, P out over P in. Max torque develop, there's two ways of doing it. You could have solved for V Thevenin, which this is kind of a pain to write down the equations. And then my R Thevenin is equal to R1 times XM over X1 plus XM squared. And then once I have that, my S max is equal to R2 over R Thevenin plus X Thevenin. Oh, I forgot to say X Thevenin is approximately equal to X1. So my X Thevenin plus X2, whoops. That's all right, my X Thevenin here. That quantity is squared. No, hold on. This is squared, and then I have to take the square root of this whole thing. And once I had S max, then my T max equation was 3 V Thevenin squared all over 2 times omega S times R Thevenin plus the square root of R Thevenin squared plus X1 plus X2 squared. That's a lot of equations, right? So that's why I gave you that MATLAB script file, which was perfectly free game to use on the test. If you didn't want to write all these equations down, you were more than welcome to just use the MATLAB script file. As long as you showed me how you got your equations, and then you said, I'm going to do a while loop, you could have just said, all right, well, from MATLAB, here's my plot, and that's Tmax. And then the last thing was T starting was your T equation that we had developed a little while ago. And then you're just going to set S equal to 0, or S equal to 1, sorry. So times that was the brute force away, or once you had that curve, you could have just pulled it right off the curve. Either one was fine. That's it for exam 3. Questions on that? Sure.
It's just the one part of P and value. Not what the unit, but if you wrote that in the number.
So let's do it this way. Let's do Sn is equal to the square root of 3 VI, okay? So we know that this is equal to the square root of 3, and the voltage is 208 at an angle of 0, and the current is 75, and the angle over here is the inverse cosine of 0.85, negative, right? So that's Sn. From there. So you want to check the actual number?
Well, no, I don't think we're. I can find that out.
Well, let's do it for the benefit of our classmates. So V is equal to 208. I is going to be equal to 75. How do I enter in magnitude and angle in MATLAB? I will have to convert it to radians, but how do I do that? 75 times, remember E to the negative J, because it's a lagging power factor, times the inverse cosine of 0.85, right? All right. When you put angle, when you go 75 at an angle of whatever, the TI is putting in it's putting in the E to the whatever, the J term. That's my value of I. If you want to check it, you take the absolute value of I. Take the angle of I, multiply it by 180 over pi. So it's 75 at an angle of minus 37.8 or 31.8, which is what we expect. Now, and I forgot the conjugate term, right? You still forget stuff. So S is equal to square root of 3 times V times the conjugate of I. So the real power is 22.97 kilowatts. Yep. And that's the test. Discussion, thoughts, comments. Is everybody bamboozled or baffled or blown away?
Thought it was a pretty straightforward exam, and you know, there's no surprises.
No surprises. Was it too hard? Was it a reasonable level of challenge, or was it too much? Okay. It's kind of cool because remember when we first started off the semester, most of you had come from John Allen's class in AC circuits. And you had all these techniques to do AC circuits. Now you're actually using it, right? Like we're doing real motors. We're actually checking motors, transformers, generators. Most of you, when you get out in the industry, I'm not saying all, but most of you will not be designing RLC circuits. That's not a put down of it. It's just that that's the reality. We're in electrical engineering technology, which is more about applications, which is taking the science and doing something with it that makes our life better. And that could mean getting power from, you know, some electrical box to power up a fan or lighting. It could be a whole host of things. Okay, so that's hopefully what you're starting to see is, wow, I actually have a lot more understanding of AC, because this entire semester was AC. There's one time we did DC, and that's for the synchronous machine. Remember DC, we have to have a synchronous machine. We usually provide it with a DC field. We hardly even analyzed that. If we had more time, we could have gone into DC motors, which are kind of interesting, but I would expect that for the vast majority of you all, you'll never come across a DC motor. And it's the same problem with DC. You know how we don't have DC electrical systems because we couldn't step up the voltages to manageable levels. DC motors and generators have lots of problems. You have commutators, you have brushes, you have slip rings. They're a lot more complicated than an AC machine. So even if we do go to a renewable energy grid, which has solar and fuel cells, you know, those put out DC. A lot of the other technologies will put out an AC, but they usually will convert to DC because it's what's called a freewheeling AC, which means it's not 60 hertz and you can't connect a non-60 hertz to a 60 hertz system. The idea or the concept is we need to be able to continue to use AC because motors are just so practical when they're AC. Even in a Tesla, right? A Tesla uses a variable reluctance synchronous generator, permanent magnet synchronous generator to do its power. So that has this massive battery. You think if they could make it work without having to convert things to AC, it'd be better off for them. But there's so many advantages to it. Just doesn't make sense. Questions? Well, I'll let you out early because I've only got 30 minutes left and it doesn't make sense to cover new material with 30 minutes. So on Thursday, it'll be an end of the semester review. We'll go over the final. We'll talk a little bit about that. I'm not going to do any exam review sheets because it's no new material. So it's going to be the first 3 exams, but I'll give you some pointers and stuff like that for the typical test questions. And it should be about the same level of rigor for the The final exam it is for one of the other exams. Does everybody know when the final exam is going to be?
Tuesday, 8 AM.
Yeah, if you haven't looked online, I'll show you this really quickly.
You know what room it's in?
What's that?
Is it in your room, Paul? Is it in? or
Yes,
is it-
so if you're gonna take
That's
it live, you're gonna do it here, but let me just show you this. Let me share my screen.
I
So here's
assume,
the final, what's that?
I assume same as usual, just email you if we would like to take the remote.
Yeah, exactly. But here's the final exam schedule for the spring. So all you need to do is go down to EET 321. So EET 321. Where is 320? Oh, up over here, sorry. So it's the second from 8 to 10 in this room. And I have nothing to do with the final exam schedule. I don't know who determines that. That's all done by somebody else. So essentially I have no control. So it's May 2nd. May 2nd is next Tuesday. But you can also check, does everybody know on Main Street, you can check your schedule? And it actually posted in there as well. So you should be able to look at that as well. So it'll be in this room. Yep. Okay. If there's nothing else, have a great day and I will see you all on Thursday. Take care, everyone.